So the last section of slides in this lecture is on software evolution. And I do want to differentiate evolution of software from maintenance. Evolution is the cumulative effect of the set of all changes made to the product after delivery. So it is not really the same thing as maintenance. This can include maintenance stuff like correcting faults, improving performance, or adding new features. It is not the same thing as a plan for maintenance, though. The idea really is to study what happens after you deploy software and you do move into maintenance to make software different from what it was originally designed to do. How does software evolve? The study of what ends up happening in terms of long-term maintenance of a software system. There are a few things that we know. For example, files increase in size in most applications, and you have an increase in the number of files in most applications. Some parts of the system end up massively churning, lots and lots of maintenance, and other parts of the system are hardly ever maintained. Churn being a word to refer to files that seem to change every time you have to make any kind of a plan or any kind of a change to the software system. And finally, all of the plans that you may have had become delocalized, meaning they end up being spread across the entirety of the system. So you may have thought, well, this one module can be done a little bit differently, but there are implications of those changes that affect other modules, and eventually the plan that you had to separate the one module from the other ends up not really working out all that well, and you end up having to have a little bit of a violation of that abstraction over time. Abstractions are great in that they help us to build software systems that are easily understandable, but as problems are encountered, sometimes those abstractions break down and the plans end up being a little bit more cluttered than we thought. Functions and software evolution. Functions change as well, and we've got a number of research studies that have found common consistent changes in functions. First of all, you end up with a larger number of functions over time. Software tends to accumulate additional functions, and very rarely are they being pruned out to the point where you're actually on net losing a total number of functions. Objects end up being created by splitting an existing object or an existing class into more than one class or more than one object. So you end up having more objects in total, even if the level of complexity of the average object decreases. Call depth increases, and I think this is the most important kind of change that you can see in software evolution, because call depth addresses the problem that most people find a little bit unintuitive as to why, if hardware continues to get faster and faster and better, does it seem that software gets slower and slower over time anyhow? Well, big piece of that is call depth. As you can do more with the software, as you can do more with the hardware, and as people expect more for existing software systems, more complexity is added, and that results in more call depth, causing the actual performance of the software, even on functions that would otherwise have been very much as imagined when the product was first released, the call depth will increase, making it less performant, feeling possibly a little bit more sluggish, and so on. So a good example of this would be something like Microsoft Word. It has tons and tons and tons of features, and so even as computers got faster and better, just opening a Microsoft Word document for the sake of editing a Word, adding words to a document or editing existing language within the document and not even taking advantage of all those other features can actually feel slower. Call graphs. We talked a little bit about call graphs in the testing lecture. They end up having specific traits that can be used to spot legacy tendencies over time, and this is something that is a very interesting piece of current software engineering research. It's the kind of thing that I don't know that we have good universal advice for people who are maintaining software yet, but as we study software evolution, I would expect that we would end up having a little bit better understanding of how call graphs can be used to help identify maintenance concerns and address those kinds of problems in the maintenance lifecycle. So what are the implications of understanding software evolution, of research for software evolution? I think there's two that are really, really important to recognize. First, software as it is maintained becomes more complex. There is more to comprehend. And so therefore, you're going to have to expect that it'll just take longer to implement features that would otherwise seem very simple to implement. in the system. So that's number one, the most important. The second most important one is that you are going to need good staff for maintenance, the best engineers available on your team if you can get them. The problem with that is that most staff, most especially experienced engineers, want to work on new things, new products, working with the latest and greatest tools and techniques. So you may actually have to pay quite a bit to get good staff for your maintenance team. That is probably still saving you money, though, because software maintenance is extremely difficult and it demands a lot from the engineers on the staff. So you get what you pay for, and in a difficult environment, it is worth paying a lot to get good staff for your maintenance team. Everything else here is very important. It's an interesting implication of understanding software evolution and some of the research that has come in software evolution. But I don't know that you could prioritize any of these other things as highly as those first two. So the delocalization of plans, modules, and functionality end up become the abstractions that we had for modules and functionality end up breaking down. And sometimes modules split in half. Functions end up being split across modules. It's a little bit difficult to track just where something might be. And this is why documentation has to be kept up to date if you look at bullet point 4, because those plans can no longer be relied on. You really need to make sure that documentation is updated as the software system evolves. Larger impacts of changes due to globalization of data happen regularly, meaning a thing that was previously just local to one module ends up effectively becoming globalized because the abstraction is breaking down. And now you have global state that has to be maintained across the entire system. Very problematic and definitely something that would violate the coupling and cohesion concerns we talked about several lectures ago. Most of the time, you're going to want to batch change requests to similar modules so that when you do end up going in to maintain that module, all of the work that's required to document and understand the module can be leveraged to fix multiple change requests, multiple problems in that module, if possible. Sometimes the urgent changes are necessary and you're not going to be able to do that sort of thing indefinitely. The as-needed strategy can be risky, especially early on, and we've got lots of research demonstrating just that this is a truism that's actually true. It is somewhat more risky to just take an as-needed strategy to understanding modules when you're doing maintenance, so definitely be aware of that. And then lastly, I wanted to talk about technical debt. This is a concept that essentially says if you have a computer program that's going to end up needing modification, and you're in the development phase, you have a choice to make. Sometimes you can implement something a cheap, quick, and easy way, knowing that down the road, when the program has to be modified, the complexity of modifying it might be much higher, or that you may end up having to rip out what you've implemented and start all over with an entirely different implementation. This is the technical debt. And it's coming from a metaphor that's financial in nature. Essentially, if you are interested in being able to develop a piece of property or build a business or do any number of other things, and you don't currently have the capital necessary to make those changes, you can borrow the capital from a bank that you could use to make those changes. But eventually, over time, you will have to pay that back with interest. Right? You'll have to pay whatever you borrow back with interest. And the same sort of thing happens with programming. When you choose to do something a quick and easy way, knowing that down the road, if you have to maintain that code, it will be more difficult and more problematic. Technical debt is a current area of research. It's just recently had its first international conference, and I think this is the kind of thing that if you've come to UMBC because it is a research university and you're interested in research, this is the kind of thing that you have a unique opportunity to really get involved with. Professor Seaman is one of the world's experts on technical debt research, and you should reach out to her if you are interested in this topic. She's an absolutely excellent researcher and very approachable, so don't hesitate to reach out to her if you are at all interested in technical debt. All right, so that's everything for our lecture on deployment and maintenance, and we will see you again next week.